When we watch a magician work, our brain completely loses track of physical reality. We get so caught up in the actions presented that we stop paying attention to where the object actually is. Let's apply that exact same trick to a mundane, everyday situation. 3 friends are sitting around a table at a rustic bar, finishing their drinks and getting ready to settle up for the night. The waiter brings over the final tab. For everything they ordered, the bill comes out to exactly 27 reals. To keep things simple, the friends decide to split it evenly. Each person pulls out a 10 real bill and drops it onto the table, creating a physical pool of 30 reals. The waiter scoops up those 3 10 real bills and heads toward the back of the room. The full 30 reals is now out of the friends' hands. Over at the register, the owner spots the transaction. Recognizing the 3 friends as longtime customers, he decides to apply a loyalty discount, dropping the true cost of their drinks to 25 reals. He takes the 30, puts it in the drawer, and hands 5 reals back to the waiter as change. Up to this exact moment in time, the physical movement of the cash and the underlying mathematics are in perfect alignment. But halfway back to the table, the waiter makes a calculated detour. Figuring the 3 friends won't easily split 5 reals anyway, he quietly slips 2 reals into his own pocket. He keeps the remaining 3 reals in his hand to return to the customers. He arrives back at the table and distributes the change, handing exactly 1 real to each of the 3 friends. This diagram shows the calculation from the friends' perspective. They each put in 10 reals and got 1 back. 10 minus 1 is 9. Multiply that by 3 and the group spent 27 reals. Here, the math gets strange. The 27 spent plus the 2 reals the waiter pocketed equals 29. We started with 30 reals. Following this logic, we can only account for 29. Where did the missing 1 real go? And why does our brain instinctively accept a mathematically impossible calculation? The answer comes down to linguistic framing. Linguistic framing is a cognitive bias where the specific words and structure used to present a problem influence how our brain decides to solve it. To break the illusion, we have to ignore the narrative entirely and rewind the scenario back to the 27 reals the friends actually spent. The flowchart shows where the money sits. The 27 real splits, 25 in the register, 2 in the waiter's pocket. The riddle adds the waiter's 2 to the 27. That is double counting. The 27 already includes the stolen money. To solve the riddle, you have to recognize that the waiter's money should be subtracted from the total spent, not added to it. It is a slice of the 27 they handed over, not an extra charge. This pie chart maps the correct equation: 25 for the register, 2 for the waiter, 3 for the friends. Merging the bars 25 and waiter's 2 gives 27 spent. Adding the friends' 3 reals of change completes the circle, returning us to 30. Back at the bar, the friends finish their drinks and head out the door, completely unaware of the mental knot they almost tied themselves into. Mathematics never lies, but as soon as we wrap those numbers in a compelling